All right, everybody. So I'm assuming you did all of this either with me in class on Wednesday or on your own when you got back. So let's talk about these questions. Hopefully, they went okay. That's the hardest, by the way. During the process of condensation, water vapor does what? This is one of those ones that you look at and you're like, I don't know. You got to know to look to the reference tables. This is why I had you circle those sections on it right there. This is straight up. Just use that table, find what they're talking about, and you got your answer. Whether you're unsure of what you're talking about or not. Let me take us to a new tab here. Let me show you on the regular one just to say there it is. There it is on the front page of the reference tables. So what do we got? During the process of condensation, just find condensation. It's right there. Energy is released, 2,260 joules per gram. Released at 2260 joules per gram. There you go. Easy for me to say. I promise that this always shows up. Give me the three greenhouse gases, or give the regions the three greenhouse gases. So in our notes, we set it right here, and it'll be there. That's just how it is. So in addition to carbon dioxide, two other ones are water vapor and methane. Choice 4. Which water cycle occurs? Process of the water cycle occurs when water absorbs 2260. So I guess they worded it slightly weird there, right? But that means that it's gaining. If it's absorbing, it's gaining 2260. Then it's vaporization, which is like what evaporation is. It's like going from the liquid to the gas. All right, we've written this enough times that we should be blue in the face. Everything that's warm in this universe gives off that like heat energy, and this is why it gets trapped here. We wrote it twice on this review sheet. We wrote it on multiple labs. We wrote it on the intro to this unit and that notes. Most of the long wave energy radiated from the Earth and lost to space on a cloudless night is infrared. Now, greenhouse gases do a good job of trapping that, which keeps us warm on the cold side of the Earth, on the dark side of the Earth. But we also are going to lose some off into space as well. Equal amounts of which surface would absorb the greatest amounts? Excuse me. First, we go between light and dark. I like dark. Light is gone. Dark absorbs more. You've worn a dark shirt on a sunny day. You realize that. And the other one that we didn't do quite as much is rough. And remember, rough surfaces, because they have more surface area, that's more available space for the surface to hold on to to grab the incoming energy. And that will absorb faster. So there you go. This was a tricky one. You have to really know your solstices. If we want the noontime angle of insolation going up every single day, well, the winter solstice, which is December 21st, coming at us soon, is when it's at its lowest angle, and then it goes up, 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 up until the summer solstice, which is June 21st. So which one of these is after the winter solstice and before the summer solstice? And your only choice is April. It's awfully tempting to go for July because it's like, July's sunny, but the days are actually getting shorter in July. Warm air rises. Yes, it does. I had a lot of people pick this one today, but that would have warm air rising here, but warm air sinking here. That's not how it works. So go for the simpler one. Warm air rises and sneaks out the top there while the cold air comes in and goes along the bottom. I like choice 4. Okay, so when you see one of these, like as we get closer and closer to the regions, we got to get better and better at getting the free points. This is an absolutely free points question. There's no reason to get this wrong. Most of the Gulf Stream is what? And you might sit there and say, okay, I think I remember the Gulf Stream. I think the answer is this. Don't do that. Get it from the 16 pages of free information that New York State gives you. There's the Gulf Stream right there. It's that arrow, which down here tells us that it's a warm current and it's heading northeast. There you go. Free points. Easy peasy. Don't try to have it memorized. Use your resources. Under identical conditions, which surface will reflect? That means not absorb. That means bounce right back the greatest amount of insulation. So we want things that are light colored and smooth, like a glacial ice sheet. Back to the ocean currents. The California ocean current flowing along the west coast of the states. California current right down there. Look at that arrow. That's this. It's cool, and it's heading southward towards the equator. Cool flowing south. Choice 2. All right, a rate of change problem. Again, if you want the 10 points, the 10% of this grade, it's got to look exactly like this. I got to see all these bits and pieces, and that's what I'm aiming for in the labs as well. You'll be given this equation that's circled. It's the change in value, how much did the values change, divided by time. Your car does this in miles per hour. You'll change this many miles in a given amount of time, miles per hour, right? We're going to do it down here in kilometers per day because it says that this hurricane moved 2,600 kilometers. So there's 2 points. You wrote down the, oh, that's not good. You wrote down the number and the label. They're both important. Over 4 days. I'm just going to go with a slightly less excited line here. So there's a point, there's a point, there's a point, there's a point, there's a point. There's 5 points already just for setting it up. I'm even throwing a point at you for the equal sign. Then you got to grab yourself a calculator. 2,600 divided by 4. 650. There's a point. And finally, the reason why I bust chops about people writing down their equations is so that the answer label shows up right in front of you. You don't have to overdo it. Just say that over that. Write down exactly what is written right there. Kilometers over days. What? Been a long day, everybody. There we go. All right. That is a 10-point answer. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 things will get you 10 points. All right. The rest of these questions actually end up being fairly similar in theme. Why does Buffalo, explain why Buffalo's surface air temperatures increase faster and earlier than the waters of Lake Erie, which is sitting right next to Buffalo? It all goes back to this idea at the top that I promised would show up a lot, and here it is showing up a lot. With its high specific heat, water heats and cools very slowly. So that's what we need. Water has a high specific heat, so it heats and cools slowly. Like around here, if you went to Port Ontario and we get one of those first days in like May, where suddenly we get it's warm and man, it's like 70. I can jump into Lake Ontario. The land got warm very quickly. That water does not get warm very quickly. If you want jumping in the spring like that, you're going to realize that fact that water is still quite cold. I'm going to hit copy on that because I think we're going to be using that again. Because if you compare the winter temperature in Watertown that's close to the water to the winter temperature in Old Forge that's far from the water, Watertown is going to be a little warmer because water has a high specific heat, so it heats and cools slowly. Speaking of that, why does the surface of Lake Erie freeze so much later? This also happens out our windows here in Pulaski. The land will freeze within a day or two of cold weather moving in. Ground's frozen. Lake Ontario doesn't freeze over, period, because it's so deep and there's so much water. Lake Erie is a lot more shallow, so it does freeze over. But guess what? Paste. It's the same thing. Because water has a high specific heat, it heats and cools slowly. So land heats and cools quickly, water heats and cools slowly. Maybe that's an important idea since your earth science teacher put it on there 3 times. What do you think? All right, excellent. Keep going on the review, and we'll see you for the test on Friday, everybody.